Good morning, everyone. Welcome to another fun-filled day of fluids. Today, we're going to be looking at mass and energy balances within fluid mechanics, once again, with specific emphasis on applications of Bernoulli's equation. So last time, when we were looking at mass and energy balances within fluids, we had developed two expressions. The first one being the continuity expression, which was an extension of a simplified mass balance when we're looking at a system where mass in is equal to mass out. We can break out these values as a function of the parameters that define the mass flow rate in these systems, those being density, flow velocity, and flow area, such that for assuming steady state, and one-dimensional flow, we can arrive at this form of the continuity equation, which allows us to understand the implications of mass flow with regards to the cross-sectional area of flow, a fluid velocity, and a fluid density. We also looked at developing the mechanical energy balance, and the generalized Bernoulli equation as a function of fluid velocity, height of the fluid, the pressure of the fluid, friction, and work. Where in certain cases, if we assume our work in friction terms are 0, we get the simplified Bernoulli equation. Which states velocity energy or kinetic energy, static energy, and pressure energy combined has to be conserved within a system. Which means if velocity changes for some reason in these systems, it either must be due to an increase of potential energy or pressure energy and vice versa.
Is that delta P over rho? I forget again, I'm sorry.
Yes, it's change in pressure, delta P over rho. And I do admit that it's very tricky to get. So let's look at a couple examples working with this mechanical energy balance today. Starting with this first one where we have N-pentane being transported from a supply tank to a storage tank through 100 feet of 3-inch piping with an overall elevation increase of 40 feet. If the mean velocity of N-pentane through the pipe is 25 feet per second, we can determine the N-pentane flow rate, both the mass flow rate and the volumetric flow rate, the power to drive the pump, and the pressure at the pump outlet. So I'll give you guys a second to jot some of that down, and then I'll work through this one with you all here in a minute. So got 100 feet length, 3-inch pipe, elevation 40 feet. So these types of examples.
We still see your PowerPoint.
Oh, thank you. I'm just trying to get it to pull up. Sometimes the share button does not appear. All right, now you should see the screen. So with these type of examples, one of the things I like to do is draw a picture because it really helps me at least visualize what's going on in the problem. So I've got a supply tank, storage tank, and I'm using a pump to transport fluid between the two. Now in the problem, it said I've got 100 feet distance. My height differential was 40 feet. The diameter of the pipe was 3 inches. And I'm transporting N-pentane, which has a density, where's my, I can't remember off the top of my head. I think it's 39. In English units. Yes, it's 39.1 pound mass per cubic foot. Let me see if there's anything else we needed. A velocity provided, said it was flowing at 25 feet per second. So with this in mind, the first thing I can solve for is the volumetric flow rate, which is the flow velocity times the cross-sectional area, which in this case would be 25 feet per second times pi times the diameter, which is 3/12 feet squared over 4. Which I should get about 1.23 cubic feet per second. Now, if I solve for the mass flow rate, simply density times the volumetric flow rate, or 39.1 pound mass per cubic foot times 1.23 cubic foot per second, which should give me approximately 48.1 pound mass per second. So what I do next is I would write out the Bernoulli expression and ask myself which values I can neglect for this calculation. Now, one of the things I also like to do is define points in terms of where I'm going to be doing the Bernoulli balance. I typically choose the top of the tank and the discharge for these types of problems. And I'm going to assume that the height differential given was mainly that the key rise necessary for the fluid to be transported from each tank. So I'm going to assume the delta Z is going to be here, or Z2 minus Z1. And I'm also going to assume both tanks are open to the atmosphere. With those assumptions in mind, one of the things I can state, if they're both open to the atmosphere, the delta P is going to be 0. Because if it's going to start atmospheric and end atmospheric, I can consider that 0. The delta Z is given, right? This is 40 feet. And I haven't said anything about friction, so for now I'm going to assume it's 0. And I'm going to say friction is negligible for right now. We'll get back to it in a second. So with this in mind, I can rewrite the expression like this: du squared over 2 plus g delta c plus work is equal to 0. Now with this in mind, I will further expand it and now input some information associated with the 2 points. So I get u2 squared minus u1 squared over 2 plus g delta times z2 minus z1 plus work is equal to 0. And what I'm looking for right now to solve for power is the work. So the question then becomes, can I cancel out anything else in this system? And based on the way I've drawn and defined the points, I would argue that the velocity at the top of the tank will be negligible, such that I can exclude it from my energy calculations. I'm going to say this is 0. I'm also going to say, as defined, that the velocity being 25 feet per second through the system, that will also be the discharge velocity. And z2 minus z1 has already been defined as 40 feet. So what I'm left with is 25 feet per second squared over 2 plus 32.2 feet per second squared times 40 feet plus W equals 0. Notice that both of these terms are positive, meaning if I'm solving for work, my work term will actually end up being negative, which is what we should be expecting because work is negative when done on the system. So if I solve for that work term by multiplying everything out and adding it together, I should end up with negative 1600.5 feet squared per second squared.
Quick question regarding this problem,
Yes.
which is when you said that the velocity would be negligible, is that going to be the initial velocity or the velocity at the top of the final tank?
It would be the initial velocity, this one here.
Okay.
That would be the negligible velocity. Realistically, it will have some velocity because assuming there's nothing coming in, it might fall a little bit. But if I'm assuming steady state to an extent, I can also argue, depending on the size of the tank, that velocity that fluid's moving is going to be really negligible as compared to the actual discharge velocity. So now I have my work, and I can solve for my power. Knowing my power is equal to my mass flow rate times work over my efficiency. So if I plug in my mass flow rate, which was 48.1 pound mass per second, let me double check that, make sure I wrote it down right, yes. Times my negative 1600.5 feet squared per second squared. My efficiency, I didn't give it. I'll just assume a value 0.8. Then one other thing I'll have to do is, and then I'll be left with pound mass feet squared per second cubed, which tells me I need to divide by G sub C, or 32.2, pound mass foot, or pound force second squared. And that will leave me in foot-pounds per second. Then I can convert that to horsepower by knowing that 550 foot-pound force per second is equal to 1 horsepower. If I run through that calculation, I should be left with approximately 5.4 horsepower.
Where'd you get the 0.8 from?
Oh, it was an assumption I just made. We could have assumed it was 1 if you would have liked. It would just be the efficiency of the pump, which for most problems I'll either specify or you can just assume is unity.
Okay, thank you.
Of course. All right, now the last part of the problem asks to calculate the pressure at the pump outlet. So what we're looking for now is the pressure at a new point, which I will then define, 0.3. Which means in order to find that pressure, I have to come up with a new energy balance, this time looking at a comparison between 0.1 and 0.3. So once again, I'm going to do my, so I'm going to say 0.1 to 0.3, d delta z plus delta p over rho plus work plus friction equals 0. Now for this one, I'm going to make some assumptions. I'm going to assume there's still no friction. Now I'm going to assume for the sake of argument that my delta z here is going to be 0. Keep being completely honest and saying there will more than likely be some level associated with the fluid in that tank. And if that was the case, I would probably give it to you in a problem, but just for the sake of illustration, I'm going to keep this simple and say it's 0. With that in mind, I'm going to look at expanding my energy balance again. And then this time, looking at the system, I'm going to say my velocity at the top of the tank is 0 also. And I'm also going to say, since I assumed that my tanks were open to the atmosphere, P1 will have a value in terms of pressure, but if I look at things in terms of gauge, I can say it's 0 gauge. And by doing that, I can simplify my equation even further. So what I'm left with then is U3 squared over 2 plus P3 over rho plus work is equal to 0. Or, plugging in the values, I can say 25 feet per second squared over 2 plus P3 over rho minus, because it's negative, 1600.5 feet squared per second squared equals 0. So if I start running through this calculation, what I'm left with is P3 over rho is equal to 1,288 feet squared per second squared, which then if I want to calculate the pressure, all I have to do is multiply by the density and do some unit conversions. So I have feet squared per second squared times the density, which was 49, excuse me, not 49, 39.1 pound mass per cubic foot. And then I just need to divide by G sub C, 32.2 pound mass foot per pound force second squared. And then I need to convert from feet squared to inches squared. I do all this, I'll get an answer in PSI G. Which I get about 10.9 PSI. Any questions on that problem? All right, I'm going to go ahead and skip this next example, which looks at bringing in friction. So I encourage you to, in your study time, take a look at example 3 in the lecture. See if you can look at how these values that have been asked change as associated with the presence of friction through the pipe. So what we're going to jump in and is look at this question, that's number 4, which asks a pump is drawing a solution of specific gravity 1.84 from a storage tank through a 3-inch Schedule 40 pipe. The velocity of the suction line is 3 feet per second, and the pump discharges through 75 feet of a 2-inch Schedule 40 pipe to an overhead tank with an elevation increase of 50 feet. And so, if the frictional losses to the entire system is 10 foot-pounds per pound, and the pump efficiency is 60%, what power is required to drive the pump? So this one's a little trickier. So we'll look at working on this one together and see what we can come up with. All right. As always, one of the things I would recommend is doing another drawing. Which I could do. So we have fluid, we have our pump, and we have our discharge to our second tank. Now, this pipe is defined as a 3-inch Schedule 40, and this second pipe is a 2-inch Schedule 40. We had defined, what else did we define in this problem? The specific gravity of the fluid is 1.84. The velocity in the suction line is 3 feet per second. So I'll say U naught is 3 feet per second. And the length of the pipe and the discharge, which when we mean by discharge, it's the pipe after the pump, is 75 feet per second. When the friction loss through the system was approximately 10 foot-pounds per force per pound, which looks like a weird unit, but I'll show you how it makes sense. And the delta Z is 50 feet. And the efficiency is only 60% or 0.6. So what we're looking for here is the power to drive the pump. So this one's a little bit of a long and complicated problem. I will most likely pick the same points, assuming my delta Z is over those points. Now, one thing we have to talk about, as it states in the problem, is what it means by schedule, pipe schedule. Now, in the back of your text, McCabe, Smith, and Harriet, in the appendices, you'll notice in Appendix 3 that it has dimensions and capacities and weights of steel pipe standard. And so for commercial piping and tubing, various types exist such that when you're looking at a given pipe diameter, the schedule has an equally important description of the pipe diameters and thickness and things like that, as along with the actual nominal pipe size given. For example, in the system, or in the appendix, which I'll write here, this is Appendix 3 in the 7th edition. A 3-inch Schedule 40 pipe has an actual inside diameter of 3.068 inches. Whereas a Schedule 80 pipe, which is another standard that it presents, only has an inner diameter of 2.9 inches. And so what the schedule refers to primarily is the pipe thickness or the wall thickness, where a higher schedule typically has a higher wall thickness. Now with that, a higher schedule has a smaller inner diameter or flow area. Now it's a bit of a pain, but the good news is in this system, as it's defined, the cross-sectional areas for flow are already defined within the table, such that if I'm looking at a 3-inch Schedule 40 pipe, the inside cross-sectional area is provided as 0.0513. So that's for schedule. 0.0513 feet squared is the cross-sectional area. The other pipe schedule it gave us in the problem was a 2-inch Schedule 40, which across the diameter is 2.067 inches. And for this one, the cross-sectional area as provided is 0.0223 square feet. So, to summarize, we have to pay attention to not only what the nominal pipe diameter is given, but also the material of construction and the schedule as presented will influence what those actual numbers should be. And so just because it says it's a 3-inch Schedule 40 pipe, the actual inner diameter is 3.068 inches, which for the sake of these problems is significant. So with that in mind, let's apply some of this to our problem. Once again, what we're going to look at is developing our energy balance, delta U squared over 2 plus G delta Z plus the pressure plus work plus friction equals 0. So in this problem, which terms can I neglect?
Pressure should be 0.
So the change in pressure, assuming everything I stated earlier, will be 0. With that in mind, I can write this out a little bit more, right? U2 squared minus U1 squared over 2 plus G Z2 minus Z1 plus work plus friction equals 0. Are there any terms here that I can neglect?
Can we say that Z1 is 0?
We can, if you'd like. Anything else?
Velocity 1.
Yeah, we can also say velocity 1, 0. Now the tricky part is it gave us the velocity in the 3-inch pipe as 3 feet per second. However, for our energy balance, we need the velocity in the discharge, which the pipe diameter is smaller. So the velocity should be higher than what's given. So to find U2, it would be U1 times A1 over A2, which equals 3 feet per second times the areas that were provided in the table, 0.05433 feet squared over 0.0223 feet squared, which should be approximately 6.61 feet per second. So now with this in mind, I can plug in my values and say I have 6.61 feet per second squared over 2 plus 32.2 feet per second squared times 50 feet plus my work, which is what I'm looking for, plus my friction, which was given as 10 foot-pound force per pound equals 0. So this is where it gets a little tricky, and this is where you have to be careful because it's problems giving you things with units that may or may not work together. So what I'm left with is work equals a negative 632 feet squared per second squared minus 10 foot-pound force per pound mass. Now these units don't match up, so what I need to do is divide this by G sub C, or 32.2 pound mass foot per pound force second squared, and then it will leave me with both values in terms of foot-pound force per pound. So if I do that division, I'm left with approximately 60.7 foot-pound force per pound for my work term. So now I can calculate my power, which is my mass flow rate times my work over my efficiency. Now I didn't give you the mass flow rate, but we can calculate it right here. And we said mass flow rate is just going to be rho UA. The density wasn't given, but the specific gravity was, which was 1.84. So the density would be 1.84 times our standard, which we're going to use water, 62.4 pound mass per cubic foot, times our velocity, which we can use either velocity with either area. I'll just use the 3 feet per second with the larger area, 0.0533 feet squared, which that gives us our mass flow rate in terms of pound mass. Per second times our work, which is negative 60.7 foot-pound force per pound mass. And then our efficiency was 0.6. And then to make that horsepower, we just divide by 550 foot-pound force per pound to get to horsepower. And so yes, it does look a little unit heavy, to say the least. So I did this calculation and I was left with approximately 3.4 horsepower. Anyone's welcome to double check my calculation. So with that, we were able to calculate our power requirements. Any questions on this example? I recommend you kind of work through it yourself to make sure you can follow all of these steps associated with doing these calculations.
When I'm trying to go through and cancel out my units to end up left with just horsepower, I still have a pound mass per second. So can you go through and walk
Sure,
us through that real quick?
of course. So first thing is that mass flow rate. So I have feet squared here in feet. That'll get rid of my cubic foot. So I'm left with pound mass per second. If I then apply this pound mass per second and I multiply it times the foot-pound force per pound mass, the pound mass will go away and I'm left with foot-pound force. Oh, that's the issue. Per second. And the unit for horsepower conversion is foot-pounds per second, not foot-pounds per pound mass. I apologize. That's why you couldn't figure it out. And so these go away. Like I said, that's why units are important and they kind of make or break you in this class. Because as we do a lot of these energy balance type calculations, it quickly becomes an alphabet soup. So I apologize for miswriting that, but glad we were able to recognize the issue and quickly address. And here I'll make that look a little neater. Any other questions or things that I can clarify? I'd be more than happy to. Okay, then let's switch gears and talk about some applications of Bernoulli's equation. The first point of discussion being looking at tank draining. Classic example I can't help but not consider. So let's say I've got a tank and it's filled with water because water's cheap to a certain height, which I will say h. So I'll say this is Z2, this is Z1, it's 0. And at the bottom of this tank is an outlet port that I can open and close. And when I open it, it discharges to the atmosphere. So in this system, I can consider it in terms of the simplified Bernoulli expression. Such that I can define things only in terms of the kinetic energy, the pressure, and the height of the system. So with that in mind, if I was going to write up this expression, which terms in my Bernoulli can I cancel or consider negligible?
Is the tank open to the atmosphere?
Yeah, we can assume the tank is open to the atmosphere. And I'm going to say my point
Does
1
that
is
mean
going to
you
be
can-
here, my point 2 is going to be here at the discharge.
Does that mean you could neglect both pressures?
So if I assume that they're both atmospheric in those 2 points, yes, I can neglect them, right? I can just say there's 0 gauge. And now those terms go away. What other values can I neglect?
C1.
You'd think, but I wrote this wrong always. So I define this as 1, which means this needs to be 2 for consistency purposes. You can define either as Z1 or Z2, but they have to be consistent. I apologize. So with the way convention I've drawn it, it wouldn't be Z1 that would be 0. It would be Z2 that would be 0, because I've defined 1 as the top of the tank. Is there anything else I can neglect?
The initial velocity.
The initial velocity. If I assume the tank is sufficiently large that as it discharges, the height, excuse me, follows very slowly. So what I'm left with, assuming my computer isn't about to crash,
Shouldn't the velocity term be squared or no?
it should, you are correct. So what I'm left with then is U2 squared over 2 equals G times Z1, which we've defined when Z1 is equal to H. That means U2, if I wanted to solve for that discharge velocity, it would simply be the square root of 2 times G times H. So the only thing I need to know to identify the velocity at discharge is the height of the fluid within the tank. One thing we also have to consider, however, is if we look close to the discharge, in a perfect world, the fluid would have a nice uniform profile. However, the fluid momentum as it leaves the tank, and depending on the geometry, often is such that the actual area for discharge, which we can kind of define like this, ends up smaller than the actual area or cross-sectional area of the outlet. And so there's almost kind of like a coalescing issue or phenomena that occurs. And it's highly dependent upon the geometry of that orifice or outlet, such that we often define what's known as a discharge coefficient, or a coefficient of contraction, that corrects for this contraction that we see as flow leaves our system. And so what we're left with is essentially a corrected expression for the velocity as it leaves or discharges to the atmosphere. Where our discharge coefficient is a function of the geometry, if I can spell geometry, of the orifice. And it usually varies from about 0.98 to 0.6. Or well-rounded orifices have high discharge coefficients. Sharp-edged orifices have closer to 0.6 in terms of those discharge coefficients. So let's look at a fun example. So a completely filled 10-foot tank, 30 feet in diameter, has a 4-inch outlet at the bottom. If the outlet is sheared off such that the water begins to flow, what would be the initial flow rate of the water, and how long would it take for the water to drain, assuming a discharge coefficient of 0.44. So, and actually, I don't like that it's 0.44. I'm going to change that because I just said that goes between 0.6 and 0.98. So I'm audibling Omaha. So we're going to say the discharge coefficient is 0.7. So for this example, I have a 10-foot tank, 30 feet in diameter. And I'm going to say the height of the water is 10 feet. The diameter of the tank is 30 feet. It's a really big tank. Now I probably need to make sure my share is going back to the lecture. And the outlet at the bottom is 4 inches. So let's look at the initial velocity of the water. Well, we can do the Bernoulli, but we already did. So I can just say U naught is equal to C sub D times the square root of 2 GH, where the initial velocity is going to be 0.7 times the square root of 2 times gravity, which I left you all in English units. Again, I know how much you love them, times the height, which was 10 feet. So this should give us an initial velocity. I'm getting 17.8 feet per second. Where if I want to solve for my initial flow rate, which I'm just going to look at volumetric, I just need to multiply by the cross-sectional area times that initial flow rate. Or pi times the diameter, 4/12 feet squared over 4 times 17.8 feet per second. So what I'm left with is about 1.55 cubic feet per second. Now, the next part is the tricky part, which is how long would it take to drain the water? So let's think about it for a little bit, and then I'll leave you with these over the weekend in terms of looking at the analysis yourself. So if I was going to completely drain the tank of water, what's going to happen to the velocity over time?
It will decrease.
So the velocity is going to decrease. And so essentially the time it takes for the height to go from 10 feet to 9 feet is going to be less than the time it takes for the water to get from 9 feet to 8 feet. And so that means is we need to identify a differential that we can integrate that can effectively describe the fluid that leaves the tank as a function of the parameters of the tank itself. And so what I would recommend you consider is how can we define a mass balance where our system is the water in the tank, and then ask ourselves, you know, M in minus M out plus M gen minus N consumed equals M accumulated. Going back to the, you know, the basics and identify which terms that we neglect, and then how can we define each term that we cannot neglect. And I think we think about that for the weekend, and then we can regroup on Monday, develop the differential, and integrate to solve. All right. And one other thing, have a great weekend all. Monday is Labor Day, so our next time we meet and discuss will most likely be on Wednesday. I might do some tweaking of module 3 just because we're just now getting into applications. So I might make next week applications and macroscopic momentum balances and pushback microscopic momentum balances. So I'll probably do some tweaking this afternoon on all of that, those assignments as necessary, and let you all know. Okay? So be looking for an email from me later on today. Any last minute burning questions? If not, I will let you all go. Thank you so much for coming into class, and I appreciate it, and I hope you all have a wonderful day.
Thanks, Dr. Lopez. Have a good weekend.
Thank you.
You too. Take care.
Thank you.